Okay, guys, this is the second part of the three lectures that we started off from 31 to 33, which were about the stereoisomerism, and we were discussing about the rules of configuration of the enantiomers and the RS convention. We discussed the first two rules in the last slide, and here is rule number 3, which states that the multiple bonds are treated as if they were an equal number of single bonds. So by multiple bonds, we mean the double and the triple bonds. So we have an example of the vinyl group, and this is what the vinyl groups looks like. Two carbons are double bonded with each other, and the hydrogens are filling up the rest of the bonds. The rule states that multiple bonds are treated as if they were equal number of single bonds. So instead of the double bond that we see here in between these carbon atoms, this double bond. So instead of the double bond, we will put in a single bond, as we can see here in the diagram. So this is the rule that we will treat it as equal number of single bonds. Plus, instead of this two bonds, we have attached two more carbons over here. So this carbon is these are the carbons that were not present in the initial, or they are not actually present, but this is just a rule for the enantiomer configuration, that we treat them as equal number of single bonds. So we will have to add up these single bonds. So instead of the two bonds joined together here, we put an additional single bond here to make up that two bonds with another carbon that we placed by ourselves, and the same case for this single bond, which is not actually present in the structure. So similarly, if a molecule has a triple bond between the carbons, we will instead place a single bond, as we have done here, and we will have to put up two more single bonds which will be attached with the carbons. Same is the case with the other carbon. We have put up these two additional bonds that I will represent with the red one. So these are not actually present, we have just assumed, or according to the rule, we have created these single bonds and the carbons that are attached with them. Similarly, this carbon is attached with the double bonded with the oxygen, so we convert that into a single bond, and then we have added up two extra single bonds. Oxygen will be with the carbon and carbon with the oxygen. So now we have understood the three rules, so we can apply them on some examples. And the example is enantiomer 3-methylhexane. This is what the structural formula looks like. So we can see one hydrogen is bonded, and three different groups are attached: a methyl group, a ethyl group, and a propyl group. So the rule that we discussed, the bigger group will have the first priority. So first up, we will assign the propyl group as number 1. Then there will be this ethyl group at 2, and then the methyl group 3, and hydrogen, which is the smallest, will come at the 4th spot. So when we arrange the molecule in such a way, we can see that we will be starting off from this propyl group, moving on in this direction towards the ethyl group, which will be second, and then the methyl group third. So when we are moving in this direction, we are basically moving in a clockwise direction, which is designated as R. It will be a R or clockwise configuration of this 3-methylhexane molecule. So it's the eye image repeated one more time so that you guys can be sure of what is happening. So the first molecule is where A has got the priority, so we go from A to B to C, and this will be a clockwise or R structure, because here is the A, we are looking from this direction. From A we move to B, and B to C, and eventually back to A. So this makes a clockwise direction in the movement of the clock. So this is a R structure. Whereas this one, when we are looking here, now the positioning of the molecule or the positioning of the groups has changed. So from A, when we move to B and then to C, we are moving in a anti-clockwise direction. Therefore, the structure will be counterclockwise, anti-clockwise, and is designated as S. Here we have a few examples where we have to assign the priority order, basically applying the three rules that we have learned. So three groups are there: uh, uh, methyl group, butyl group, a hydrogen atom, and the amino group. So rule number one was that if atom other than the carbon is present, then we will have to give it priority according to the or in any atom present or joined with the carbon, we will have to give priority according to the atomic number. So nitrogen has the highest atomic number, that is why it is given the first priority. Then the biggest group present is this one, so we give this one the priority at second position. Then the methyl group and hydrogen, which has got only one atomic number, is at the last position in the first example. Moving on to the second one, again the same case, oxygen will be given priority because of high atomic number, but this oxygen has got a methyl group or a bigger group attached with it, so this is at 1, whereas the oxygen and H or the hydroxyl group is at position number 2 because it has got a smaller other atom attached with it. Then comes the nitrogen, which has got a lower atomic number than the oxygen, so this NHCH3 group comes after it, and then the CH2NH2 group at the end of the order. Now this one, the third example, has got a fluorine, which has got highest atomic number, so it comes first. Then the hydroxyl because of the oxygen, then CH2OH, which is a bigger group and has got oxygen in it, and then at the end is the methyl group, which is the smallest in this case. Here we have an example of the multiple bond. So which group has the priority, isopropyl or the vinyl group? And vinyl group in this case has got higher priority because of the double bond present in it. So the vinyl group we just discussed a few slides ago, that the double bonded carbon will be treated as if it is attached with the 2 extra carbons. So that will make up a total of 4 carbons, which is much higher than the isopropyl 3 carbons. Therefore, the the vinyl group takes the priority. Next up are some examples with these multiple bonds present. So here is the example, and we have to arrange them according to the priority order. And in this case, the aldehyde group, which is double bonded with the oxygen, will get the highest priority because we assume that this double bonded oxygen is actually bonded to 2 oxygens with single atom. So this makes this group or the atomic number much higher. Then will come the CH2OH group, which has at least 1 oxygen. Then the CH2 group, which is our vinyl group, and at the end will come the ethyl group, which does not have any double bond in it. So here we have a couple of more examples where we have to determine the configuration, whether it's R or S at the stereogenic center or the chiral carbon. So here we have the central carbon, and it is attached with 4 different groups, as we can see: hydroxyl, aldehyde, and propyl group. Now the hydroxyl group will take the priority or the first position, whereas the aldehyde group will take the second position. Now a confusing point can be that there is a double bond here, so it gets attached with 2 different oxygens. Why doesn't this aldehyde groups takes the priority? But the reason is that in the case of hydroxyl group, the carbon is directly bonded with the oxygen, and the atomic number of the atom which is bonded with the central carbon takes the priority always, whereas in the aldehyde group the carbon is bonded with another carbon, that will always take the second priority even if there is a double bond present with the oxygen here. And the third priority will be of the propyl group, which is the third carbon basically. And so because of this double bonded oxygen, this aldehyde groups takes priority over the propyl group because there is no oxygen present in this one. So we will go from 1, 2 to 3, and it will be a clockwise or R configuration. Whereas in the second example, again carbon is bonded with the nitrogen, so the amino or nitro groups takes the first priority, then the phenyl group takes the second one, and the methyl groups takes the third priority. So we go in counterclockwise direction. This is a S configuration. So on this slide, the name is given, and we have to draw the structure basically. So it's R2 bromobutane, and we have to draw the structure. So first up, we draw the regular structure of butane, which has got 4 carbons in it, and we fill up the number of hydrogens, and at the second position we attach the bromine atom to make it a 2-bromobutane. Now this carbon in the which has got a star at top of it, this is our chiral carbon, this one here, right here. This is the chiral carbon. So around this we have to draw the proper structure. So this carbon is attached with one hydrogen, this one, and then this ethyl group on one side, then methyl group on the other side, and the bromine atom as well. So writing these groups in priority, the bromine has got highest atomic number, so it takes first the priority. Second comes the ethyl group, which is bigger than the methyl group, and the hydrogen with the lowest atomic number comes at last. So we draw the structure and attach the hydrogen with it. Then at position 1 we put in bromine, at position 2 we will put the ethyl group, and position 3 we will put in the methyl group. So we can number these in any way we want. The hydrogen will always be at the 4th position, so we can start off basically with any of these numbers. It doesn't matter whether bromine is put at the top, at the bottom, or on the left side, but the order of rotation will always be the same from bromine to ethyl group and towards the methyl group. So this will be a clockwise rotation, and hence it is the R structure. Next up is draw the structure of S2-phenyl butane. So again it's a butane with 4 carbons, and it has got a phenyl group, a ethyl group, a methyl group, and the hydrogen atom. The main difference is in place of the bromine we have taken the phenyl group, which is represented by C6H5, and that will take the first priority as it is the biggest group present. So C6H5 takes the first position, second position goes to the C2H3, and third to the methyl group. So this one will always be going in the anti-clockwise direction from 1 to 2 to 3. That is why it's a S structure. Next up are the physical properties of the enantiomers that we just discussed, the non-superimposable mirror images of each other. So the physical properties are first up, and these enantiomers will always have the same melting point, boiling point, density, and spectroscopy. So main physical properties are always the same for both the S and the R variety, and the difference is usually the biological and physiological properties, or you can say their function can be totally different inside the body, and the arrangement of atoms or the group of atoms in space will also be different. Obviously, that is why they are the enantiomers. So the example given is R lactic acid and S lactic acid. Lactic acid is acid that is produced usually in the muscles when we are exercising. So it's a byproduct, and its accumulation basically causes the pain in the muscles. When you have done the exercise for a long period of time, everybody feels the pain, and that pain is usually due to this acidity that is caused by this acetic acid. Anyways, both the R and the S variety will have the same melting point, as we can see, 53 degrees Celsius, but their arrangement of atom in the space is what is different. They are super non-imposable mirror images of each other. Next up are Fisher projection formulas. So they are a special type of formulas that are particularly used in biochemistry. So Fisher projection is a type of two-dimensional formula of the same molecules that we saw, the three-dimensional formulas. If it is a two-dimensional formula of a molecule which is used to represent the 3D configuration of the stereogenic center or the chiral centers, then we call it Fisher projection. And as I said, they are used extensively in biochemistry as well as in carbohydrate chemistry. So the main rule of this Fisher projection is that we have to arrange the molecule in such a way that the horizontal bonds, as we can see in the diagram, the horizontal bonds are with the chlorine and with the bromine around this chiral center, which is the chiral carbon. So the horizontal bonds at the chiral center will be pointing towards U. So they are like projecting towards us, whereas the vertical bonds are pointing away from us. So the hydrogen and the fluorine are away from us, whereas the bromine and the chlorine are towards us. So when we apply these Fisher projections to the actual molecules, it will look something like this. So we have the structure A, B, C, and D are the two attached groups. And just for the sake of example, we have taken a bromine, a chlorine, hydrogen, and fluorine, like in the previous slide as well. So bromine takes the first position, chlorine the second one, and the third one is fluorine according to the atomic number, and hydrogen is the smallest one. So this will be from 1 to 2 to 3, and this will be a clockwise configuration or R configuration. And the main rule, as we saw in the previous slide, is that the horizontal bonds or the atoms or the horizontal bonds are projected outwards or towards us basically, whereas the vertical bonds are towards the back or away from us. So some more examples of these enantiomers. Again, the same thing. We have to find out the configuration of these enantiomers. So we simply have to tell whether it's a R clockwise configuration or a counterclockwise S configuration. So looking at the first one, chlorine has the highest atomic number. Then will come the ethyl group, then the methyl group, and at the end the hydrogen. So going from 1 to 2 to 3, this will give a clockwise or R configuration. Second one, we have oxygen attached, so this will take the first priority, then the same ethyl group and the methyl group. So going from 1 to 2 to 3, this gives us a counterclockwise or anti-clockwise S configuration. Again, the one at the bottom, hydroxyl group, and the methyl group, ethyl group first and then the methyl group. So this will give us a you can say S configuration, whereas if we put the atoms in this arrangement, then it will be known as the R configuration. So here we have the compounds with more than one stereogenic centers, which is also called as diastereomers. And for such molecules, we have got a formula to calculate the number of stereoisomers. The number of stereoisomers is represented by this formula, 2 raised to power n. where N is the number of chiral centers or chiral carbons in most often scenarios. So we've got a compound 2-bromo-3-chlorobutane, and as we can see with the stars, there are two carbons in the middle that are both chiral carbons. So if we put in the formula 2 raised to power n, which in this case is equal to 2 carbons, it will become 2 raised to power 2, and the total of 4 stereoisomers will be present in case of 2-bromo chlorobutane. And at carbon number 2 we can have the R and S configurations, and at carbon number 3 as well. So do remember this formula for calculating the stereoisomers. The structure can be there in the exam, and you have to tell how many stereoisomers are there. First you have to check how many chiral carbons are there. Simply put in the formula 2 raised to power n, and you get the number which is the stereoisomers. So here we have the 2-bromo-3-chlorobutane, a similar structure like the previous slide, which has got two chiral carbons, and a total of 4 combinations can be there. Therefore we can have 4 stereoisomers which we can calculate from the 2 raised to power n formula as well. Now looking at the possibilities that this second carbon can be of R configuration, so we get a 2R and a 3R combination, that both second and third carbon are of the R configurations, whereas both of these can be S configuration as well, so 2S and 3S will be the structure. Then we can have on the second carbon there is R configuration, but on the third one we have S. So 2R and 3S is the third possibility, and 2S and 3R is the is the fourth possibility. Sorry. So there are 4 combinations basically depending upon both the carbons in this scenario. Therefore, 4 stereoisomers will be the result. So this one is a continuation of the previous slide. As we said that 4 different combinations can be there for this molecule of butane, and which are represented in this scenario. Now the thing to remember is that all the relationships or all the combinations are not enantiomers of each other, or we can say they are not enantiomeric. Only 2 of these are enantiomers of each other, the 2R, 3R, and 2S and 3S, whereas these 2 are also enantiomers, that is 2R and 3S with the 2S and 3R. But these 2 and the other combinations, these are not enantiomers. The stereoisomers that are not enantiomers, that is the definition of diastereomers. So diastereomers are a little bit different from the enantiomers. They are stereoisomers, but we do not classify them as enantiomers. So they will be similar to each other in the structural formula, but the identical chemical and physical properties will not be there, which is the case for only enantiomers. So the same thing explained here. The 2R3R combination and 2R3S combination are not enantiomers because they are not mirror images of each other. As we can see that around the carbon number 2, the configuration is exactly the same. Bromine is on the left and carbon is on the right, so they cannot be mirror images of each other, so we cannot call them enantiomers. So what do we call them? These are known as diastereomers. So diastereomers are the stereoisomers that are not mirror images of each other. Next up is something that we call meso compounds. So we see the same example, 2,3-dichlorobutane, not the same one, sorry, 2,3-dichlorobutane is the molecule here, and it can have these 2 configurations, which will be enantiomers because they have chiral centers, and they are mirror images of each other, these 2, so we can call them enantiomers. Whereas on the right side we have got a mesoform. Now what is a mesoform? It is achiral because if we put the plane of symmetry in this case, if we divide these molecules into two parts, the two parts are exactly equal to each other. They are identical. So we call them identical achiral, and the important name used for such a molecule is the mesoforms. So this structure and its mirror images are basically the same, which we call the mesoform. They are identical. So mesoform is basically a achiral molecule that has got chirality centers in it. There are some chiral centers present in it, but overall the molecule is known as achiral. Last slide is about the stereoisomers of tartaric acid. So it has got two chiral carbons. So putting in the formula, we will have a total of four stereoisomers. There can be different configurations seen, as in this case RR configuration, SS configuration, whereas the RS configuration in this case will also be the mesoform or achiral. As we can see, it has got a different melting point, whereas these two on the left are enantiomers of each other with the same melting point, 170 degrees Celsius.